Yeah, so already spoiler alert there, sorry. Today I will show you our work regarding the complex samples, and thanks a lot for the nice introduction. Both talks this morning was perfect for us to start with. So after the talks, I will have to explain to you how we can control the microstructure using laser power fusion, and we can clearly and locally control the crystallographic texture in particular. I will talk now about the austenitic stainless steel, and as you may know, the deformation mechanism in this material is strongly dependent on the emission and the deformation crystallographic texture, and also on the logarithmic path. So in a standard tensile test, we know that if we have a 1-1-1 texture along the logarithmic direction, we will have an enhanced strip effect, which leads to a strong material. In the other side, if we have a 1-0 texture, the trips effect will be suppressed unless we have a less strong material. So this opens the possibility, of course, to tailor locally the crystallographic texture in order to enhance or suppress local transformation accordingly for the requirements, in particular for one particular component. So the question is, can we build these complex samples with locally different material properties and therefore superior performance? So in order to start working with this, we decided to start with this kind of core shell structures by using a modified surface in the core and in the shell in order to have a hard surface and a soft core, or the other way around. Regarding how the process parameter optimization was done and how these materials behave in uniform texture, there were two nice posters from my colleagues, so I hope you've seen it yesterday. Going straight to the sample printing strategy, as Matteo already told us and really nicely explained. In this case, we decided to go for this kind of strategy. We have in the layer number M, let's say, for this kind of core and shell structure, when you have in the inner part of the sample a 100 along the loading direction, which is in this direction. We have scanning strategy going back and forward in this way, and if we want to have a 1-1-1 texture along the same direction, we change the angle at 55 degrees, as in this case. So the sample was built one on top of the other, following this kind of shape. These samples were built at EMPA using pre-alloy 304 pulp. So after that, we machined out some dog bones to perform our tensile test. The microstructural characterization of the sample clearly shows that we can achieve these core shell structures with locally 1-1-1 texture in the loading direction at the shell and 1-0-0 texture along the loading direction in the core. So we did some in situ neutron diffraction measurement at Poldi, at the Bolshoi Institute. And as you can see here, this is the incoming beam. We have the detector there, and the loading direction is in this direction. For each loading step, we place a small gauge volume at the core and in the shell, and we move the sample around in order to see how the deformation behavior was in the shell and in the core. The main issue with this technique is that the volume, the martensitic volume fraction was really low, so it was basically not possible to detect this with neutron diffraction, so we have to move to a different technique. Again, we have a magnetic phase, the martensitic is magnetic, so we use polarized neutron imaging to perform this experiment. I will talk really fast about the technique. Basically, we have an incoming neutron beam, which spin up and down, and after a polarizer, we choose up, let's say. So if you have a magnetic sample in an external field, we basically measure with an analyzer how is the depolarization of the beam due to a magnetic phase in the sample. By doing this in a bidimensional way, if we have no magnetic structures in our sample, we will have one, all the neutrons go through without any depolarization. But if we have a magnetic sample in front of the beam, we have this kind of contrast in the image. And we can do that with a 30 microns spatial resolution. So we did this in situ. Again, this is the experimental photo. You have the incoming beam in this direction, the loading direction is here, and this was done at BOA. beamline also at the Bolshoi Institute. So going straight to the result, this is the samples with a 111 core and 100 shell, and you can see here how when we, as the strain is going up, the contrast of the sample is appearing. So we have a martensitic, clearly a martensitic phase in our sample. So in this case, we can use this technique to detect really low volume fraction of martensite. We'll go in and we give more detail regarding the different samples that we study. In these cases, this is the one that I already showed you, and you can see clearly that in the inner part of the sample we have more depolarization, which means more martensite. And in this other case, when the shell is actually the 111, is more or less uniform. If you take a look of the profile in this line, this aligned profile of the two samples for the same strain value, you can clearly see the same effect. In this case, we have a lower depolarization here at the center, and in this case, we have a lower value here at the shell. But how we can quantify this, right? So in order to quantify the samples, we have to take into consideration that we are using a transmission technique. So it's a convolution between shell and core, so we have to deconvolute both effects. In particular, we have to perform some geometrical correction, and also we have to correlate this depolarization with the amount of martensite. In order to do so, we use uniform samples and also a sample with random texture, and after the measurement, we take the ferritoscope to characterize the volume fraction corresponding to the green color or the depolarization value. After the calibration and after the deconvolution of the two parts, we can see here how the volume fraction evolved as a function of strain, and we can clearly see that for the blue part, the 111 part, we have more trip effect, more martensite fraction, and we can have the same behavior for both core and shell correspondingly. Going to the post-mortem in BSD, this is a really nice picture when you can clearly see that the blue grains, even in the core, we have a lot of martensite, while the red grains are completely out of martensite. We also have a lot of twinning, as you can see here from the BSD. And we can conclude in this case that it's a significantly more trip effect in 111 grains than in 100, that was exactly our assumption. Going straight to the mechanical data, this is how the two samples behave. And this is clearly the dependence of the 111 and 100 texture is clearly following our assumptions, as also the work handling here. You can compare them, and if you put how the complex samples behave, is exactly in between both. So we can create this composite. And of course, more trip and trip, we have a stronger work handling. This could be used also to characterize more complex materials. We did some FDA. Actually, it was our intern, Mamasar intern was working in this. He used ANSYS, and we performed this kind of simulation when you can see clearly that the experimental curve follow really nicely how the simulation predict. That means that we can use this information to create more complex samples, and we already have the technique to do it. So going straight to the conclusion, I hope I can show you that neutrons are a really interesting technique to characterize your samples, and I really encourage you to do that. But also going straight to my conclusion, we built complex specimens with local crystallographic texture, and the volume fraction that we have after the deformation was really low, and it was below the limit that neutron diffraction could extract, so we went to a different technique, which is polarized neutron imaging. And by doing this, we can clearly quantify the magnetic volume fraction with spatial resolution. The post-mortem EBSD showed the trip and significant trip effect. And also, we now have a model with finite element analysis that could be used to create more complex structures. So with that, I really thank you, all my collaborators, and your attention. Thank you so much.